is Dan Cascaval, and I'm here to talk to you today about differentiable 3D CAD programs for bidirectional editing. So lots of engineering computer-aided design is done using so-called history-based CAD models. These are essentially scalar functions from scalar parameters that generate geometry. And they have a different number of parameters controlling every operation, and the user can later go back and edit these parameters in order to make changes to the model. This kind of programmatic CAD model is used very widely in engineering, and it's really good for that application, primarily because it defines a design space with constraints. And in a context like engineering and fabrication, allowing arbitrary geometric deformation isn't necessarily desirable, because the actual set of designs that we want to explore, say the ones that are fabricable, is vanishingly small compared to the set of all possible configurations of geometry. Moreover, such models are nice because editing them can be very easy. In that engineers, if the model is constructed correctly, can simply tweak some parameters and produce large geometric changes that would be laborious to specify directly by editing all of the geometry into exactly the desired configuration. However, working with programmatic CAD models in this way isn't perfect. Parameterizations might be difficult to understand, or it might not directly correspond to an edit that you want to make. For example, in the context of this camera mount model, if we want to make even a model that is this simple, uniformly thicker, we start to having to edit multiple parameters at the same time. For example, here, in order to make the whole thing thicker, we have to edit the height of the initial rectangle and the distance that we extrude, that we make the chamfer. As a result, there are ways in which we can mess this up if we edit only one parameter at a time. And if we go far enough, we start having to edit more parameters in order to continue making the same semantic edit. As a result, there's a lot of overhead for a designer to keep track of multiple parameters and how they're changing in order to make an edit. So we'd like to offer a bit of a better interface to solve this problem. So in our system, we prefer to take a bidirectional approach where the user can make edits to the parameters when this is desirable. But in other cases, they're able to specify their intent by dragging around some vertices in the model, allowing them to specify geometrically what they want to happen, and have the system update the program such that it generates the geometry that the user has indicated. This is bidirectional as opposed to just inverse, because the user can always go back. Notably, if we were to just naively edit the generated geometry, we would get our result, but we wouldn't be able to go then back and have a program generate that same geometry. As a result, users can edit models without the previous downsides. We do this by defining the models in an automatically differentiable domain-specific language for CAD and use the derivatives in order to return optimization results interactively. Additionally, we will highlight a number of issues relating to performance and ambiguity that are present in such a system and in how we chose to approach them. However, geometrically driven editing has obviously been done before. So what's different about our approach? So one previous work in this area a few years ago was called iWires and focuses on heuristically inferring structure, inferring some wires from a geometric model that correspond to structures and features that should be preserved in the geometry, translating user inputs into edits on the wires, and determining how to propagate edits through the wires, which then very neatly edits the overall mesh. So this work heuristically infers structure. So it's very generically applicable. It doesn't require an underlying program and can work on pretty much any model, but comes with no guarantee that the result will meet any predefined existing design space. More recent work in Graph last year focuses on models that do have a program associated with them, specified as a DAG of CAD operations. And users can inverse edit this using a brush by dragging on the mesh and specifying how they would like an area of the mesh to change. And so this uses pre-authored models and a finite difference-based automatic differentiation, and can even handle very generic edits that include topological changes through Boolean operations in the program. Our work takes a different approach. We demonstrate different ways of dealing with ambiguity compared to this work, and illustrate a way of constructing a system that can't handle topological changes, but is able to handle models that haven't been at all pre-authored for editing. So if you think back to our example before, right, in order to make a model pre-authored for editing, an author would have to think about every possible way that a user might want to change what they're designing, which is sometimes very difficult to do. So we'd like to have some methods that show how we can do this without having the program be predefined with a small number of parameters that are all relatively orthogonal. Instead, our method works on programs that have many parameters that might be redundant or conflicting. So how do we do such a thing? There's a couple of challenges in doing it. The first is that a user edit might be infeasible, in that if the user drags some vertices, there might not be a program that directly corresponds to the vertices where the user put that. And this happens all the time due to the nature of the specification, because the user is dragging vertices. That's fundamentally an inexact operation, and you always have a little bit of error here and there. It's very difficult to get an exact solution. The other problem is ambiguity, which is also happens all the time, where sure, maybe there's no one perfect solution, but there's many equally good solutions. Right, so the user has said what they want to happen to some vertices in the model, but we don't know what should happen to all of the rest of them. There might be many different sets of program parameters that all put the vertices where the user wants, and this happens more often the fewer vertices the user selects, namely the more convenient the operation is. So we'd like to have a good solution to this. How do we do it? So the way that our system works is that, well, think normally. So when you edit a CAD program, it runs, it generates the geometry, and that's about it. You can change the parameters and generate more geometry, but if you manually edit the geometry, your changes go away. So in our system, when you edit the program, the interpreter generates the geometry, but it also keeps track of a computation graph of the program. This graph is almost entirely composed of operators whose derivatives we know how to compute. From this graph, we can then compile functions to native code that represent both the normal execution of the function and the gradient. Because it's native code and don't have to actually generate any of the geometry, they're really fast to evaluate, so we can use them in the middle of an optimization loop. So we use optimization of a version of our objectives, which tell us how close to a certain set of parameters is to satisfying a given user edit, right? So the edit is specified as a movement of model vertices, and we would like a function that tells us, okay, how close are you and which direction should you go? And so allowing the solver to call these in the inner loop allows us to conduct a fully global nonlinear optimization at relatively interactive rates. And this optimization, we run several different optimizations with several different heuristics, which generate many possible results for ambiguous edits, which are then returned to the user, and then they can select between them. The user selecting them causes the parameters to be modified, and the process starts again, allowing users to quickly edit, select, and iterate towards their desired goal. A computation graph is built as the program executes. So each time an operation is called, our interpreter knows what graph nodes to add and link together. In this example, the user is chamfering the corner of a rectangle and extruding the resulting angled edge. So we maintain an explicit formula for the position of each geometric element, the vertices in this case, in the result in terms of the input geometric elements, and we build up a corresponding graph. So this is really just keeping track of all of the arithmetic operations at the granularity of individual scalars. There's a couple of things to understand about this. So first of all is the fact that some operations have constraints. For example, the radius of the chamfer shouldn't exceed the length of the edges that are being adjacent to the chamfered vertex, or it would end up creating non-manifold geometry. So as a result, we implement something to prevent this using equality constraints, where the constraint is defined as a number that is greater than 0 if it is satisfied. So you can see that as the G2 and G3 in this example. And this allows us to compute not only a vector of constraints for a given parameter point, namely, are the constraints satisfied or not, but also a corresponding matrix of constraint gradients, which allows the solver to converge much more quickly. Please see our paper for details of this. Nodes in the graph are never changed or deleted. Even if the geometry they correspond to is removed at a later stage in the program, they're still part of the history of the computation. For example, V3 in this example is removed by the chamfer from the geometry, but it's still part of the formula of the resulting vertices V4 and V5 and V6. If the vertex is truly unused, then it will end up being optimized away in the compilation process. And the last thing to note is the fact that this graph is static. So the same graph will be produced by any numeric parameters you pass into the same program. So this is why the compilation process works, right? Because you can evaluate the compiled function to any parameter point. Otherwise, you would have to redo differentiation, regenerate a new graph to be computed at potentially every optimization step, which would make it much slower than it is now, and potentially not allow us to achieve interactive rates. So the trade-off for this performance is that we lose the ability to handle topological variation, right? Since we have an explicit formula for every element in the output in terms of the graph, and the graph must be the same, the output must also always look the same in that every vertex will be generated with the same connectivity in the same order for every single possible set of parameters you could pass to this function. All right, so we've mentioned optimizing program parameters towards an objective quite a few times now. So let's take a closer look at what these objectives actually are that we're optimizing. So the primary metric that we optimize is simple edit distance. We want to find parameters that minimize the L2 distance of the vertices the program generates from where the user edited them to be. Note, this isn't all of the vertices, just the ones that were selected and moved. We refer to this as an edit distance and is a component of every single optimization that we run. On its own, this already does an okay job, and with gradient descent, you sometimes get a solution that's pretty close to your starting point. So we can see an example of running this naive optimization on this model of a castle where the user drags one of the towers, and you can see that it does achieve the result in that the tower moves to where you want it to be. However, there are kind of arbitrary changes happening to the rest of the model, right? You can see some of the other towers are getting wider, some crenellation spacing is happening, the walls are changing their thicknesses, and it's in general kind of very unpredictable and difficult to control exactly what will happen in this kind of case. But it's a promising start, and it happens to be reasonably performant, so we decided to go in this direction. Moreover, it handles the infeasibility problem relatively well, in that if there isn't quite the exact configuration to produce the user's edit, gradient descent will usually get you pretty close, even just following edit distance. The other problem, however, is that it doesn't really handle ambiguity, right? There's still many possible parameter combinations, and gradient descent here is really just choosing an arbitrary one. To address this, we introduce a number of other disambiguation heuristics to regularize the optimization. The objectives include simple energies like minimizing the distance of vertices the user didn't select from their starting positions, or preserving all of the edge length. We experiment here with a localization term on top of a pairwise matching of the vertices from their initial positions. So here we localize each vertex's contribution to the overall energy based on its geodesic distance from where the user, from the vertices that the user had selected. This means that we end up penalizing vertices that are closer to the user's selection moving a little less than we penalize vertices that are farther away. And this happens to greatly mitigate random stuff happening elsewhere in the model away from where the user edited. We then compose this localized vertex objective with the initial edit objective with a different sort of weight gamut that has been chosen differently by us empirically for every one of the objectives that we present. So there's a similar setup in the paper for all of the other energies, which include things like edge length preservation, program parameters, and so on and so forth. We present a number of different energies here. We also demonstrate that existing methods from geometry processing are applicable in this system and can be applied to create success as regularizers. For example, think of the case of minimizing a biharmonic energy or producing an as rigid as possible transformation that is still within the space of the output of the program parameters. So this is super powerful because it confers all of the nice geometric properties associated with those kinds of energies while maintaining the geometric constraints enforced by the program. But it's not quite trivial to do. For example, if we were to do it naively, right, say that we have a vertex edit and we solve for that edit purely geometrically using one of these, say the biharmonic objective, we would get the figure in option B. If we then later use those vertex positions that came in option B as the input to the edit optimization, we would end up with option C. And this is not quite so good, right? But if we compose the biharmonic energy objective with the actual geometric program and optimize directly on the program parameters as opposed to doing two separate optimizations for the vertex positions and then the edit, then we end up with a much smoother result. And this program is very interesting because that constraint is specified nowhere explicitly, right? What is happening here is that each of the rings is obviously flat, but then the top and the bottom rings share the same XY parameters. So the constraint that is there latent in the program is exposed and optimized through by this biharmonic energy. So our paper contains more of the details on this, and we'll look at some of the results produced by some of these energies here. And I'll note that a lot of the energies are chosen largely with the goal of producing results that are different from one another, rather than for one or the other to be the exact optimal solution the user is looking for. So this works out pretty well. Because the more different they are, the more likely the user is to get an option that is close to what they were looking for. And if there is absolutely no result that is close to what they were looking for, then there's also a benefit because the user can identify by comparing the differences between the results, which vertices need to be specified further. Where do I need to tell the system what to do? And what should I do in my next iteration to keep working towards my goal? So let's look at the results. Here the user is editing a model of a bench and fixing the vertices on the bottom left leg in place and moving the vertices on the top right of the chair up into more of a chair shape. And we see what the results are of the different optimizations here. So we see that initially the vertex energy, that is the kind of most naive thing you could do, doesn't do quite so well here. It does some strange things. It flattens out the top of the chair. It makes the seat very thin. And this is because it's trying to keep those vertices lower, right? As we make the overall model higher, the vertices that were previously on the seat and top of the chair want to stay closer physically to where they are, regardless of the global context of the model. And so it ends up making these somewhat strange deformations. If we use, say, the biharmonic energy, which preserves the kind of local transformations, we end up getting a much better result. All right. That really preserves kind of the global overall structure of the chair, such that it resembles the original bench, but now contains the desired form. Another objective that we experimented with is the parameter energy, which minimizes an L1 distance and parameter space from the starting point. In this case, it turns out to be a pretty decent proxy for creating a chair, and it's very cheap to evaluate because it doesn't have to look at any geometry at all, right, and delivers almost comparable results. Here we have an example where the user is editing a model of a lamp in order to move the edges of one of the lampshades out in space a little bit. Right, so we introduce an objective that preserves the center of mass of an overall model. So this can be meaningful on some models where the center of mass matters to the fabricability and you would like to preserve it, and this is one of them. And we note that this offers a lot more freedom than some of the other objectives, right? Because only the center of mass, which is somewhat of a summary statistic, has to be preserved, the individual geometry is allowed to vary more widely and find solutions that otherwise wouldn't be found. Looking at the other optimizations, the minimizing biharmonic energy allows the tubes to be stretched much more because most of the sort of conjunctions of vertices look locally similar, even though the global scope of the model is allowed to change. In the case of the parameter optimization, because it's an L1 optimization, the optimizer finds that it can change a single parameter, namely the angle of the initial lamp, in order to do pretty much all of the work, right? And this moves a lot of geometric elements in a way that the other optimizations are kind of disinclined to do. But it results in an edit that a human can understand. It might point out a model parameter that the user might be interested in working with directly. The vertex objective, without the localization term, tries to keep light bulbs, which are spheres and have many vertices, as close to their starts as possible, and errs on the side of moving all of the light bulbs a little bit so that the light bulb closer to the edit doesn't have to move too far from its initial position. In some sense, it's getting a little bit distracted here by the fact that vertices are much more dense on some areas of the model than others, which leads to irregularization that doesn't really correspond semantically to the object being edited. When editing a slipper, we can see that both the vertex and the edge losses are affected by this density of elements in the model when using a mesh representation. For example, the vertices on the toe are much more dense than elsewhere in the model, so the vertex optimization prefers to keep the vertices on the ring of the toe near where the spheric joints, closer to where they usually were, and ends up just stretching everything out a little bit, noticing that the back of the model can be kept completely static. The edge optimization notices that there are, again, many more edges on the toe of the slipper, and prefers to just edit this sort of ring of edges along the sole to make the whole thing a little bit thicker and keep almost every other edge the same length as it used to be. We also introduce a heuristic that preserves volume, which is interesting in this case because you can see how it subtracts some of the volume from the sole of the slipper and puts it into the heel in order to make the edit that makes it larger, and even ends up making the base of the heel narrower, right? So again, this doesn't necessarily work well on all models, but where it does can end up exploring part of the design space that would otherwise not be necessarily intuitive to get to, but might correspond to a user's goals with respect to a given model. So we tried this on a few users, and we didn't run a formal study, but we did survey some real-world CAD users to see what they thought, right? How did they use the interface, and what can we learn from that? So there's a couple of main takeaways. So it's easy to find nice variations of the model and explore the design space because this is what all the objectives are doing, right? Users said that they felt like they were sculpting rather than using traditional CAD, right? They also found it easy to make quick edits and one-off changes and test and ideate. However, it wasn't all sunshine and roses. There's still some challenges. Right? It's hard to fix an element in place. For example, you can select vertices to try to fix them like we did with the chair example earlier. But the optimizer might still move them ever so slightly in order to get a solution that it thinks is globally closer to what you wanted. Similarly, it's hard to maintain exact dimensions. For example, if an edge should be of length exactly 3, which is exactly the kind of thing CAD users are used to saying, it's hard to do that because of the same problems. Right? You might end up changing by a couple epsilons or so. And it's very hard for users that are used to traditional CAD, but this kind of thing is exact and analytical, to get used to this more informal and loose way of specifying, and not at all incorrectly, because when your objective is fabrication, you actually do need exact dimensions. Finally, it was hard to understand for users when they dragged something and edit they were expecting to occur didn't occur in any of the options. In all cases that this happened, it was because the specified configuration that the user had made wasn't achievable or even remotely approximable by any parameter combination in the existing program. This caused the optimizer to not really get any close to the objective at all and deliver kind of random solutions. This kind of poses a pretty big usability question moving forward, which is what happens when you really can't do it? How do we show people what can't happen? Right? The takeaway that we found in surveying users for this was that it's much easier to debug stuff when it's changing and it shouldn't, rather than when it should be changing and it doesn't. Right? It's easier to see breakage and respond to it, to see ambiguity and respond to it, and iterate towards a solution than it is to explore a space that seems unwilling to be explored. Moving forward, we'd like to see this work unified with some of the other methods that we mentioned before to get a broadly applicable and performant inverse editing system for CAD programs. This paper proposes one way to differentiate a class of CAD models for real-time optimization, but one could imagine similar methods that merge geometry processing optimizations in CAD models to enable a design process that is augmented with new editing automations like the ones we presented, as well as other work that enables the incorporation of topological changes or physical simulations and other functions that are difficult to reason about, but end up making a huge difference to the impact of designs when they're ultimately manufactured and used in the real world.